Welcome to Dozochem. This video covers polarity of molecules. A nonpolar covalent bond occurs between two nonmetals that have the same electronegativity, and that means the electrons will be equally attracted to both atoms. Whereas a polar covalent bond, the two nonmetals you're bonding have different electronegativities, so the bonding electrons will be more attracted to the atom that has the higher electronegativity. And in parentheses here, just a reminder that the closer the element is to F on the periodic table, the higher electronegativity it will have. So down below just shows you a sketch of a bond between iodine and fluorine. Since fluorine has the higher electronegativity, the electrons will be more attracted towards the fluorine, and sometimes you'll see an arrow to represent that. The head of the arrow pointing towards fluorine means the electrons are more attracted in that direction, and the plus end of the arrow tells you that the electrons are less attracted to the atom on that end, in this case, iodine. So if you look at the Lewis structure for carbon dioxide, we know from Vesper theory that it's going to be linear. And remember, in the sketch, we don't distinguish between single or double bonds. We just show the three atoms in the same line. So each of these bonds is a polar covalent bond because C and O have different electronegativities, and because the electronegativity of oxygen's much higher than carbon, you would show the head of the arrow going towards the oxygens and the plus end of the arrows on the carbon side to show that the electrons are less attracted towards carbon. However, even though you have both polar covalent bonds, there's no overall attraction of the electrons in one specific direction. You can't say that they're more attracted to the left or the right or towards the one oxygen or the other. So because there's no overall attraction of electrons in a specific direction, you would say the molecule has no dipole moment, or you could use the adjective that the molecule is non-polar. Now let's look at the example of water. Here's the Lewis structure. Two bonds, two lone pairs makes it a bent molecule, so you can see the sketch here. And each of the bonds is polar covalent because oxygen has a much higher electronegativity than hydrogen. So the heads of the arrows are pointing towards the oxygen. Now in this case, you can pick a direction that the electrons are attracted towards. You can't say left or right, but you can certainly see they're both attracted upwards towards the oxygen. So this red arrow shows the overall direction of attraction. So if there is an overall attraction in one specific direction, then you would say the molecule has a dipole moment, or you could use the adjective, call it a polar molecule. So to summarize, if the arrows basically cancel each other out and there's no specific direction that the electrons are shifted, you would say it's a nonpolar molecule, or it has no dipole moment. And if there is a specific direction that you can say the electrons are shifted, then you would say it has a dipole moment or it's a polar molecule. So we can summarize in general and say that molecules with no lone pairs on the center atom will be nonpolar, and molecules with lone pairs on the center atom will be polar. It's that simple. However, I put an asterisk here. The one exception when you have no lone pairs on the center atom would be if the outer atoms are different nonmetals, then it will still be a polar molecule. So down below I show an example of an atom A bonded to two different atoms on the outside, X and Y, and even though A doesn't have a lone pair on it, so it's linear, because of the different atoms on the outside, and up here I'm just noting that X has a higher electronegativity than Y, which has a higher electronegativity than A. This polar covalent bond between A and X has a large difference in electronegativity, so the electrons are strongly shifted towards the X atom. The other bond is polar covalent because Y has a higher electronegativity, but it's not quite as strong in attraction towards the Y. So even though the arrows are going in opposite directions, the shift of electrons isn't as strong equally strong in both directions. So there's an overall shift towards the X atom on the left. So even though there's no lone pairs, there is an overall shift towards the X. So because there's different outer elements, you would say it's a polar molecule. So that's your one exception. So this table, you probably saw this before in the VSEPR video. It's the same 3 columns as in the VSEPR video with the VSEPR notation, name of the molecular geometry or shape, and bond angle in the first 3 columns. So the only new thing is adding a 4th column to tell you whether it's going to be polar or non-polar based on its VSEPR notation. And you'll see the common theme is that the ones without lone pairs, so the ones that don't have these E's on them, are going to be non-polar, and the ones with the lone pairs are going to be polar. And then there's asterisks, just reminding you that you might have no lone pairs, but it will still be polar if you have different nonmetals on the outside. So that's it for this video. Good luck.